Alright, here's our infrared distance sensor. You can see what it looks like physically. It only has 3 pins. And it's designed to work, at least this particular model, from about 10 centimeters to about 80 centimeters. And you can see that at 10 centimeters, it should give you about 2.3 volts. At 20, let's say about 1.3. At 30, maybe 0.9. At 50, about 0.6 approximately. And 80 or let's say 60, about 0.5 volts. So what we developed is a line equation to be able to calculate the information. And you can see here that this is our experimental data. We measured at 10, 20, 30, up to 60. And then we let Excel give us a line equation, which is this value here. And then we used it in our program. So in our program, you can see I've added this line, which represents the equation, to give us the distance in centimeters based on voltage. It seems to work out quite well for us. Now, one of the issues is that you may need to add a low pass filter. And these are the calculations for a low pass filter. And we want to have a cutoff frequency of about 22 Hertz. And to do that, you can use a 15K resistor and a 0.47 microfarad capacitor. And here's the difference that you get when you add that low pass filter. This is the input to the filter, and all these little spikes represent higher frequencies. And this is the clean output from the output of that low pass filter. Now, when you are measuring that, you should turn trigger off, make it equal to none, so that we can measure that, because there won't be any trigger points in this signal. Hello, this is our Arduino code to average and plot the distance from an infrared distance sensor, actually the sharp infrared distance sensor. So I start off by having a global variable called A0 integer on this line. I run the setup, but the main reason for the setup is just to set up the serial port to 9600 bits per second. And then I go into my main loop, and it's fairly short. It's only from lines 5 to 21, and within that loop I have a for loop. But before I actually run the for loop, I'm going to initialize a variable called total, which is an integer variable, so that I can use it for obtaining averages. So what I want to be able to do is that this infrared sensor can be a little bit noisy. So to filter out that noise, a good technique is to use averaging. A second technique is actually use analog filtering, and we'll look at that as well. But using this technique is easy, simple, and fast. So what I'm doing here is I'm going to read the analog sensor on line number 8, and I'm going to read it 8 times. Okay, and I'm going to start off on this first line, which has a count that is initially equal to 0. And then it's going to continue to count until it reaches a value that's less than 10. And it automatically increments using the count plus plus, which is an auto increment instruction. And it just runs from line 7 to 10, and then it repeats 10 times. And what it's going to do is read the analog input from the distance sensor, add it to total, do this 10 times, and then on line 12, once we're out of the for loop, it's going to divide that information by 10. Line 13 converts it to a voltage, and on line 14 we use the equation for the line that we determined by experimentally measuring the distance at different points. And then on line 16 to 20, what we're doing here is we're going to actually use something called a plotter. And what it allows me to do is to plot information on something that looks like a scope. And what I'm telling the system is that the maximum value I want to have is 60, minimum is 0, and then we're going to display distance in between that. And you must use the format that's shown here. So maximum 60, quote, a space in quotes, 0, which is the minimum, a space in quotes, and then print line the distance. Okay, and once we do that, you're going to see that we get a graph. So let me see if I can set that up. So I'm going to just pause the video. And to be able to use the serial plotter, you have to click on this little icon over here. That's the serial plotter. So I'm going to click on that. So here's my serial plotter at 10 centimeters from the sensor, about 20 centimeters from the sensor, and this is about 30 centimeters from the sensor. Hello, here we're doing a basic test of distance for the 2Y0A21 sensor. It has a range of about 10 to 80 centimeters. So I'm starting off at the 10 centimeter mark. Hopefully you can see that down there. And my software is reading about 2.4 volts, representing a distance of about 9.6 centimeters. And I also have a meter attached, and it's reading about the same voltage that I'm getting on the screen. So what I'm going to do next is move this over to the 20 centimeter mark. And you can see right there that this is 20 centimeters. My sensor's over here. And my screen is reading about about 1.4 volts. And my meter is reading 1.36. To round it off, it's 1.4. Now I'll move this over to 30 centimeters. Okay, it's the 30 centimeter mark right there. My meter's reading 0.98. And in my software on the screen, about 1 volt, so very, very close. And that's the distance from here over to 30 centimeters. Let's go to 40. That's the 40 centimeter mark. I'm getting 0.77 from the screen, about 0.81, very close. And the sensor is over here, going all the way to the 40 centimeter mark. Let's go to 50, which is right there, 50 centimeters. My meter reading 0.65, and my computer reading 0.71. So as I get closer, I'm going to get more accurate meter and computer reading results, but as I go further away, they'll become less accurate. Okay, that's it for the demo.